been pretty close to like what we covered in that. So I'm pretty sure what we'd actually go, this part right over here would be what was gone over in that. Subsequent stuff is stuff that was not covered in that. It's a little more contemporary and like things that was kind of released. But in any event, little bit of a background here. All right, so you're going to go to the URL.
Oh, yeah, okay.
Yeah. So this basically uses like a gradient boosted machine as an API. And so when you fill out the form, I'll start sharing here. It basically, one second, let me present. Okay, it pretty much just kind of pings that, and then like you get the predictions back and things like that. And so, can you see my screen, Jake?
No, you're kind of grayed out.
I'm grayed out. Okay. Okay, that's turning off the camera. Give me 1 second here. Okay. Okay, present. All right. Yeah. So the idea then.
Oh, yeah, there we go.
Okay. Yeah. So the idea then, so this thing right over here, you fill out a form. So kind of your different characteristics of what situation you're in terms of either you're pulled over, you're being searched, or your search is over, and then whether or not you get arrested or searched. Okay, you can play around over here and play some different values. So like you could put in your own demographics and things like that. Okay, and like if you are searched, you can basically put why it happened, and then because of that, go ahead. All right, run analysis. Okay, and so here, if you get pulled over for suspicious movement under these circumstances, this person, your chances actually look pretty grim for getting arrested. And then so basically, this right over here is like what gradient boosting does. You get this number. And then what goes into this right over here is basically all the contributions to the final prediction. So there are basically 4 different models that it connects to. So depending on what you do here, you actually go ahead and access like a different model that's basically pickled and then stored in a server somewhere. And then you see this number right over here. And then what is stored down here, this is something that was not covered in class. And then we'll go over that probably 2 weeks from now. And so it's a newer technique that allows you to take pretty much like any model, like a neural network or a GBM or something like that, and then kind of like decompose it into kind of its individual contributions. So yeah, if you have a single prediction, what does each column kind of contribute to the final outcome that you're looking at?
So is it kind of like a cross between like feature importance and partial dependence?
It is, but it's actually done at a local level, which is important. So for a single prediction, you can then kind of go ahead and then take a look at it.
Interesting. Okay.
Yeah. So feature importance and then partial dependence are all global, like for the entire data set. Like kind of like what's important, things like that. This kind of allows you to break it down for like a single unique example.
Interesting.
Yeah. So for whatever it's worth, it was released a couple years ago. It's called SHAP. It's gotten pretty popular because it's a good way to kind of understand and decompose like the nonlinear, non-parametric models that are used for machine learning. So
make it a little bit less like black box.
Yeah, exactly, that kind of thing. And so
cool.
So yeah, that's it. So we'll talk about like that because it's a pretty useful contemporary technique, and then it's for people who use like boosting and neural nets and things like that. It's become pretty widely adopted because it kind of allows it to behave more like more traditional statistical models. Linear regression or not?
Sorry, you just cut out there.
I'm not sure if you're familiar with linear regression or not.
Oh, I mean, in like a 3 years ago kind of sense. But
okay, yeah, like maybe you took like something on data camp for like a couple of weeks or something like that. I don't know exactly, but okay. Yeah, like linear regression is a really popular modeling technique because for any single prediction, you can actually take like and break it down to see its individual contributions to it and things like that. And so in practice, people really like that because if you're predicting it's going to be XYZ value tomorrow or next week, you can kind of like quantify like what every unique like column is contributing to it. But this kind of allows you to do the same thing. But boosting tends to give you better results, so you're usually kind of gives you the best of both worlds. But in any event, okay, this thing was trained on a data set of about 4.5 million samples. They're all taken from North Carolina. If you want to go and download it.
Sure.
Let me post a link.
So I'm trying to do a split screen here. So
yeah, sure. No, take your time. I'll give you a few minutes.
Okay. I'm ashamed to say I don't have a Kaggle account.
Yeah, it's no shame in that. Honestly, I never really got into it too much.
I feel like it's good practice, is what I've heard.
It is good practice. Yeah, it has lots of little nuggets and resources and things like that. It's also a good place to keep track of newer trends and libraries and things like that. So I like to kind of keep track of that. That's actually very useful because, I mean, the newer techniques or packages or whatever tend to bubble up pretty quickly there, and so if you kind of browse through different notebooks, the actual competitions themselves can take up huge amounts of time. So unless you really kind of enjoy that competitive aspect where you're just kind of like pounding away at like a data set, they kind of squeeze out like a last five or last percentage of accuracy. To in my opinion, it's a little soul sucking. Like I don't really have I don't have the temperament to really get into that, things like that. And so because it's usually the case, you can get about 98% of the results after a few hours, and then the next 100, are collecting everything after that, and then some if you look at the actual leaderboard for competitions, things like that, like the top couple hundred people, a lot of times are just separated by a fraction of a percent, things like that. So
wow. Okay.
So whether or not you actually want to go through that much effort to kind of get something like that modest improvement, it doesn't track very well to real life in my experience, where you just typically find something that works and stuff like that, and then you get better stuff to do than to spend dozens and dozens of hours trying to squeeze out the last couple
just a little bit more. Yeah.
So it's not really my thing, but some people like it.
Yeah, I mean, it seems like it'd be useful to go through a couple times and see how close you can get to the top, but not.
Yeah, it does kind of expose you to some different types of problems and data sets and things like that. So it's good that way. But yeah, I've usually though after about 5 or 10 hours, and I feel like I've kind of gotten to that point where it's about there. My drive to keep going with it just kind of gets sapped pretty quickly.
Yeah, that makes total sense. Okay, so I've got this CSV, and I think when I tried to open it, it popped open Excel, so that's gonna.
Okay, yeah. So as long as you have it downloaded on your computer, you should be fine. Yeah. So give me 1 second here.
I'm there.
All right. So what we can do here is go ahead and then take a look at the notebook where it says not the lab, but the other thing.
Police X-ray modeling walk.
Yeah.
Okay.
That one. 1 second. Let me find it here.
Okay. No sweat.
I forget. Am I still recording, Jake?
Yeah. Looks like yeah. You're good.
Okay. I'm not recording. Am I sharing my screen? Sorry.
Not.
No. All right. Okay. Give me 1 second here. All righty. So we'll do this, that. All right. So what we'll do here, this will just kind of be. This isn't entirely what was done, but kind of the starter code, for what was done. And then different variations done for this, like the different models used for it. And so in any event, all right, so I'll share now. Do you have the notebook opened up?
Yes.
Okay. All right. So the idea here, only thing you'd really need to do is just, put in your own file path right here.
Okay.
For the file itself. And so once you do that, you should just be able to run through everything else.
Okay.
In fact, let me get out of this.
Hey, there it goes. Okay.
Okay, great.
Awesome. All right. Yeah, for whatever reason that took a minute, but
yeah, sure, no, it's okay. Actually, let me close out of this and open it back up. I was
Speak of the devil, it's raining. I gotta close the window in a sec.
Yeah, sure. Yeah, no problem. Take your time. Where am I? Okay. So let me get this thing. Just do base. All right, let's do that. No, remind me later. Let's launch.
Awesome.
All right, so let's go ahead. OneDrive. Here's use X-ray. Okay. All right. So, all right, let's go ahead. Load this thing in. Okay. So this thing is a formatted version of about 5 different data sets for different cities in North Carolina. And so the basic idea here, city they're pulled over in, age, their race, sex, whether or not they were arrested, if they were searched, whether or not contraband was found, okay? And then the idea is NAN basically means they weren't searched, okay? Because this column is only relevant if the search itself was actually conducted. So here, whether or not they were searched, if they were searched, the reason why, if the reason they were pulled over, okay, and then finally, these are the different reasons someone may have been searched. The majority of people were basically only searched once, but there are a few folks who were probably particularly, on their bad behavior, who got searched for multiple reasons. Okay, so conceivably, someone could have, a couple of true columns over here. Okay, hour of the day, day of the week, and the quarter. Okay, and then the idea then. All right, so that's the data set.
Okay. And this is just for like car stops, essentially?
Yes.
Or people getting pulled over? Okay.
Yeah, people getting pulled over. Yeah, just car stops. So yeah, some person kind of patrolling, like a city center, things like that, it wouldn't be located. As far as I know, yeah, I don't think so. I think it's just, just car stops.
Okay.
Okay. Hopefully, I hope these 2 libraries are pretty familiar. XGBoost and category encoders.
Yeah, I remember those.
Yeah. Okay. All right. An area of familiarity to them. Okay. So real quick, so we're doing XGBoost. So in this case, just for performance reasons, we're just sampling 250,000 samples because 4 million would take a little while. It takes maybe, depending on your computer, like anywhere from 10 to 25 minutes for it to go through and run. So it's not really good for an example. And so basically what we're doing here is, if you go over here, again, between the scenarios and the outcomes, there are basically 4 different ones you could potentially do. Okay. And so each one includes different sort of subsets of information. But this one is just the very beginning. So the idea is you're pulled over. You don't know if a search has been conducted yet or not. Okay. So essentially, the idea then, if I can find it here, this info, like whether or not someone was searched, the reason why, okay, or something over here like this would not actually be made available to you yet. Okay, because it is basically information as you are pulled over, like the police officers walking to the car, things like that. So I don't really know what's going to happen yet. The idea is you sort of want to capture like the relative impact of different things at different stages. Because one of the things that's tricky about these sorts of problems is that lots of times, certain events happen in a certain sequence. And so the idea behind this is sort of capture different aspects of the process to kind of see as you kind of move forward through it and more information is made available. How do the relative importance of different things eventually change and stuff like that?
Yeah.
Okay. So in this case, just for this particular example, it's really just as you're pulled over and like the police officer's walking to the car and you don't know anything else, but really, so all this really like is made available to you is why you're pulled over, and then characteristics of like the time and place, and then characteristics about you. Okay. So like, this, where you're located at, time of the day, things like that. Like if you're black, white, if you're 21 or 38, things like that.
Yeah.
Okay. All right. But nothing particular about why a police officer may have decided to have, gone further about something. Okay. So in any event, all right. So what we're doing over here, we're defining the columns: city, subject age, subject race, subject sex, reason for stop, hour, day of week, quarter. These would basically correspond to the things you could fill in if you were here. Okay, like this too, and then these are the things you can go ahead and fill out. Okay, so that basically are, right, the columns that you see defined there. Let me go ahead and find it. Okay, training, test, and splits. Okay, so training sets and test sets. Okay, we're initializing XGBoost. Okay, some of these things should be pretty familiar, right? So tree depth of 3, learning rate of 0.05. This is a parameter that wasn't covered too much in class. It's not incredibly important. The idea is, if you remember, with gradient boosting, you start off with a naive estimate and then you kind of update it from there.
Yeah.
So the idea is the default baseline value you go by is the 0.5 for a classifier. So the probability is 50% and sort of like updates that after every subsequent round. If you want to, you can actually specify what the base score is going to be when it starts off with. So in this case, if you look at the notebook, it's basically defining it as the average search rate for the data set, which is something like 0.03.
Oh, interesting. Okay, and then does that just make it more, I guess, effective? I guess like
it speeds up convergence. Basically, if you start with like 0.5, you would still eventually get to the same results, but you would probably just require more boosting rounds to get there.
Yeah.
So it just kind of shaves off the number of rounds you might need to get to your final result before it turns off.
Yeah. Okay.
Okay. So that's really what it. So it just makes things a bit quicker. It's not terribly important. Again, you kind of get the same thing, but you might be able to use 10 to 15% less rounds to get to the final answer. We're doing early stopping. Okay. So we're adding in a pretty large amount of boosting rounds that we're probably not going to have to use. And then we are balancing the classes. Okay. So people get searched about. Yeah, Jacob, do you have a question?
No, sorry, I'm probably just taking notes in the comments.
Okay. Yeah, sure. I'm not sure. Basically, if you remember, this is basically how much you want to penalize the model for misclassifying the minority class. And so the idea is taking the inverse of its average occurrence. Basically, we'll just give it equal weight to non-searches.
Gotcha.
Okay. So therefore, just in terms of how you're treating each of the classes. To the model itself, even though searches only occur about 3 or 4% of the time, to the model, they pretty much have, it's like a 50-50 split in terms of the overall penalty or loss they're contributing during the training process. And then binary logistic, this is basically kind of like the standard. Like if you're doing binary classification, this is the loss function you typically use right over here. Okay. Happy to answer any questions.
Okay. Let's see. So sorry. Let's see. For the output, I guess, or like the outcome variable. So right now we're trying to say, was a search conducted true or false, essentially?
Yes. Yep. Was a search conducted true or false?
Okay. Gotcha. Okay. I'll have to kind of revisit my notes on the like penalizing or like the balancing part, but I do remember that concept generally. I just don't remember.
Yeah. So I'll give you a little bit of a refresher here. Welcome, Sylvia.
Hello.
How are you?
I'm fine. How are you?
Oh, doing great.
Did you start already?
Yeah, we started.
Okay.
Okay. Okay, so we're probably actually it's probably fine to talk about it now, if you don't mind. I mean, if everyone's okay with it. So basic idea, if you remember, so gradient boosting, you fit your model on the gradient, which is basically the derivative of the loss function. Okay, with respect to your model's predictions. And so for regression, it comes out to basically the error column. For binary logistic regression, it's not quite the error, it's close to it, but it's something like the error exponentiated some kind of value or things like that. Okay, so the idea then, okay, the overall size of the error that you fit the model on, you literally multiply it by that value entered into scale positively. Okay.
That's for essentially like you said misidentifying the minority class, right? So like specifically if let's say the minority class in this case is searched is true, then if the model says like, hey, the true result is true, but I say it's false, then we're penalizing that more harshly so that we can
exactly so like the error from that prediction is going to get multiplied by like 25. Because searches happen about 4% of the time. So 1 divided by 0.04 is 25. Or searches happen about 4% of the time. So the inverse of that is 25. So therefore, if whatever the error is on the prediction, you would multiply that by 25, and that would go into your gradient for the next round.
Gotcha. Okay. So basically, we're making the false negatives count as much as the false positives.
Yeah, exactly. Like in terms of the total amount of error that the model's actually looking at, there's an equal amount contributed by each of the classes. Okay. So therefore, they're given equal importance. That's the basic idea. It's usually kind of a standard if you're doing these sorts of things. So that way, if you have imbalanced data, like the model basically sees it on equal footing.
Yeah.
And so you could potentially use different values of this to get better results. It's not necessarily like if you're trying to maximize predictive accuracy, you could actually try something different. But as kind of a first pass, equal weighting is usually like a pretty standard approach that most of the time you can stick with. But you can maybe on your own experiment with something else if you wanted to. All right, hey Sylvia, real quick to get you up and running here. The modeling walkthrough notebook, we're going through it now, and then we are pretty much on this part right over here. Okay. And so we're getting ready to go ahead and then run the results. But if you need a few minutes, Sylvia, just to kind of go ahead and get yourself caught up, feel free to let me know.
Okay.
Okay. So if that's a yes, we're happy to grant you a few minutes, if you need a little bit of time just to kind of get everything loaded in. All right. Well, as a courtesy, I'll give you a minute here. All right, and then we'll just kind of casually shoot the breeze here, relax. Give you a moment, and then we'll go from there.
I just opened the notebook.
Okay. Okay.
I thought that you will start from the beginning again.
We did.
Repeat everything. Okay.
Yeah, we did. You came a little late, things like that. So we're about maybe 1/3 of the way through the notebook. Just let me know in your good spot. Again, here, just if you want to see it, Sylvia.
Which part are you talking about? Oh.
Yeah, sure. We're basically in this cell right here.
On 12. Okay.
Yeah. And then Jacob here. So basically here, if you look at this, this is why. Maybe I didn't actually run this. Hold on. So this is why I train. That's the average value. So 1 divided by that, is 20.38. And so basically what this means then
you're essentially multiplying the error by
that value.
Yeah. Okay.
And then that's the value you go ahead and put the model on. And so that basically means like the total amount of error contributed by each of the classes would be equal.
Would be equal. Okay. Yeah, that makes sense.
And then the big benefit of that is you're much more sensitive to changing conditions that might affect the positive class.
Yeah. Okay. I think we were talking about this before. We were using like a medical example, right? If we're looking for like cancer in some sort of data, and like that was a relatively rare occurrence, but you wanted to detect it with
exactly
certainty.
Yeah. So the idea is it just makes you sure, like if this particular like instance were to actually occur in the first place, you'd actually want to be able to make sure like your model had like some capacity to actually see it, and like sort of understand what might go into causing it and things like that. Because otherwise, the overall loss contributed by the majority class will typically overwhelm everything else, and so your overall accuracy will actually go down doing this because you're going to start generating a lot more false positives. But it does mean though, like if to the effect that like some kind of circumstance or collection of circumstances would cause like some positive event to happen, your model will be much more likely to pick up on it and be sensitive to its changes.
Yeah. Okay.
So you wouldn't necessarily want to do this in every circumstance, but it's actually fairly common. The thing you actually want to be able to classify is not occurring very frequently.
Yeah.
Okay. All right. Sylvia, how you doing?
I'm just checking the document, but I think I don't have the correct version. I need start. I need download again.
Yeah, sure. The link here is in the chat. I'm not sure if you can see it or not.
Because I opened just from the last one, so I am going again back.
Everything from the last batch, Sylvia, should work the same way.
Yeah, but I started the new notebook, so I don't have everything there. So I need to go back to your notebook.
Okay. Yeah, just let me know when you're ready.
So I guess looking ahead just a little bit, when we're talking about pipelines, I thought for some reason we didn't have the ability to use pipelines and early stopping. Like I thought those were.
Yeah, I actually don't think we do in this one. Let me double check here. I could be wrong. Yeah, so we're using pipelines here to transform the data, and then we're taking the transformed data and then feeding it directly into XGBoost.
Oh, okay. Gotcha. So we're just using the pipeline to do the
yeah. And so that way you're transforming the validation set according to the training set, stuff like that, and going into that. But yeah, and then you're doing this right over here.
Gotcha. Okay.
Yeah. Okay. One other thing that's worth pointing out over here is the criteria that was used to evaluate everything. It's called area under the precision recall curve. It's similar to the F1 score, but it actually measures the F1 score over different probability thresholds. We'll talk about what that means in a minute here.
Okay.
Okay. It's maybe a slightly more holistic way of looking at a model compared to just like the F1 score, the reasons we'll talk about.
Can you remind me what the F1 score is? Can you please remind me what the F1 score is?
Yeah, sure. All right. This is kind of like a DAT like refresher for you, right?
Yeah,
yeah. All right, getting like all the stuff. Yeah, you kind of in the back of your head somewhere, things like that. Yeah. So the real quick here. So some basic notes. So you have precision, which is true positive. Okay. Divided by true positive plus false negative. Okay. So the idea here, actually, excuse me, no, it is false positive. Okay. So precision, all right, is what you'd call the positive predictive accuracy. All right. So the idea here, this is the correct number of identifications of the minority class that your model made. This is the total number of times that your model predicted something would be that particular class.
Okay.
Okay. So essentially, the way you should think about this, of all the times your model predicted like something is going to be this particular category, how often was that prediction actually correct?
Yeah. Okay.
Okay. Okay. And then recall, true positive divided by true positive, and then the difference over here is the false negative. Okay. And so the false negative right over here basically means it was an instance of the positive class, but your model mistakenly thought it was nothing at all. Okay. So essentially, the false negative right over here, this is basically the number of samples that kind of slipped through the cracks, so to speak. Okay.
So like of all the true positives
that existed,
right? How
many of them did your model detect? Okay. For whatever it's worth, usually the more heavily you weight the minority class, usually the better your recall is going to get. Okay, because you'll have less false negatives, and then your model will be more aggressive in recommending the positive class, and so therefore this number will tend to go up. Okay, so usually, yeah, if you were to compare like overall accuracy with kind of like unweighted classes, right, where they weren't touched at all, there's a good chance the precision would be not so bad, but the recall would be pretty terrible. And then the more heavily you weight the minority class, the more you see this number would go up, because you would basically predict a positive class more frequently because you're more sensitive to it. Okay. And Jake, you sound like you are frantically just trying to like rack your brain for, like what happened like 2 or 3 months ago and things like that, like all these sort of like metrics and that kind of stuff. You know, so like
100%.
Yeah.
Sorry.
All right, Sylvia, are you doing okay? Okay, in this case would be you have a notebook, and then you have the modeling walkthrough notebook loaded in, and you can run the individual cells.
Yes, I ran, and But the notebook cells has different numbers on my notebook.
That's actually okay, Sylvia. You don't have to worry about that so much, to be
Because
honest.
I'm now on a cell 7. It's going import pipeline, but I'm not sure if I am on the correct space, because you're
probably fine. If you don't mind, let's circle back to the actual notebook itself. So where we're at in the notebook here, Sylvia, is if you can run this thing right here. Okay, like that's where we left off.
It's about classifier. Okay, I will check.
Yeah. So if you can run that cell and just kind of it goes through correctly, it should be fine. You shouldn't have to worry about these things on the left-hand side, just as long as the cell itself runs.
So yes, I ran this XGB classifier. Okay. Thank you.
You're welcome. Okay. All right. So real quick here. So we're gonna have a tree depth of 3, learning rate of 0.05, which is pretty small. We're gonna start the model instead of having 50% chance of one class or the other, with the average value of y, with the idea that this will just cause things to converge a little faster. 5,000 boosting rounds, which is almost certainly too many, but we're using early stopping. We are scaling. Okay. Rather, we're weighting the positive, the positive label to basically make sure it has equal weights with the negative one, and then we're basically supplying the loss function for binary classification. Okay. Real quick here. Target encoding and then one-hot encoding. I'm happy to answer any questions if we need a little bit of a brush up on that.
I think we're good on that one.
Okay. Sylvia, I'm happy to provide clarification for it if you want to know more detail what it is.
I just remember that the one-hot encoder, it's like for each value in the data, it's making a new column. And
that's correct. That's correct. Target encoding here, okay, is a little different than that. Okay, so target encoding, what it'll do. Just real quickly, one little demonstration here. Okay, so Sylvia here, what target encoding will do is instead of doing one-hot encoding, right, we get a separate column for each unique value. Okay, target encoding, okay, will basically transform something according to the average value of the target variable for that particular column. Okay, so in this case, if we were to look where for city, right, it turns into 0.020928. Okay, it means the average search rate in Winston-Salem was this number. Okay, and then the average search rate in Charlotte was 0.056979. Okay, and then the average search rate in Greensboro was this one right over here. And so likewise, the average search rate for people who get pulled over for a vehicle violation is 0.04. And then the people who get pulled over for speeding, the average search rate is 0.018. Okay, so it's just a different way of transforming categorical values into numbers. Sometimes it can be actually a little more accurate than just standard one-hot encoding.
And how we choose which column will be used for the average value?
Yeah, sure. Usually, where you typically would want to use target encoding, Sylvia, is if you have a fairly large number of unique values. That's where one-hot encoding sometimes can kind of get you in trouble, because when your data set gets particularly wide, sometimes one-hot encoding, you have so few samples for each of the individual columns that it can be difficult to kind of generate useful inference from each one. And so keeping everything in a single column can be a bit more helpful. So as a kind of a standard rule of thumb, if you have anywhere from about 2 to 3 dozen unique values in a column, it's often a good idea just to go ahead and target encode it.
I understand that the one-hot encoder is not good, or I don't like it because it's making too many columns. But
yeah, it makes a lot of columns. It kind of it really expands your data set.
So when we put here like a name of columns, city, and reason for stop,
yeah,
how we doing that name of column which we are taking for the average value?
Okay, repeat that question, Sylvia.
When I'm looking on the parameters for target encoding, I see only city and reason for stop. I think that we are changing this column to the something better, but
we're basically transforming this according to the average arrest search rate for each of these 2 columns.
Yeah, and where we are setting that name of column for the average value.
Yeah, so you mean basically where are we deciding where to one-hot encode something? Is that sort of what you're getting at?
You said we are taking average value for, I think, no reason for stop. I'm thinking where these numbers came from. Which column we counted for that average value?
Yeah, sure. So really here, real quickly here, ready? Where these numbers come from? See if I can do this. Okay, and then don't. It's not going to work. Okay. There's a way to do this here. But the basic idea here city is no, that's not going to work. Okay, so real quickly here. Let me try this real quickly. So where they're coming from. Here, position indexers are out of bounds. That's no fun. All right. So x train dot index x dot index. Don't mind me, Sylvia, where I just kind of stumble through this stuff. Give me 1 second here, okay?
Okay.
Okay. I still think this should work. So it's not clear.
Would you want to do this on DF instead of X?
Why not? Let's just try it. I think actually probably should work, but
I was just thinking that X wouldn't have the search conducted value.
Yeah, you're right. You're probably right about that. One thing that's a little struggling with me is all these index positions should actually be inside DF. So it's a little bit of a curiosity to me that it's because X-train is basically coming from DF. So why exactly Okay, 1 second. I don't want to belabor this point too much. Let's try this. I think it's because some of these things are greater than 250,000. I think that's the problem that we're running into. So let me just try something here very quickly here. I think that's the problem. Okay, you do not have to do this. I'm just sort of just adding this to make sure these things work correctly. And then here, let's give it a shot. Okay, there we go. But we went ahead. Actually, drop should be true. Okay. All right. Ooh, now we still have that index column. All right, so give me 1 minute here. All right, and then let me just take a look. Okay, all right. So, all right, this works. Okay, so Sylvia, so the idea here, okay, this is the data that's inside the training set, right over here.
Yeah.
Okay. Okay. So, are you familiar with the group by operation in pandas?
In SQL, but I think it's the same.
Okay. Yeah, it's actually, yeah. In SQL, it's the same as in SQL. Okay. Okay, so the idea then, all right, if you're to look at our training data, Sylvia, group by each of the city, and then look at the average value, basically the average search rate for each of the individual cities, you'll get these numbers here.
And yes, and these numbers, these are which column, which value are you taking from which
yeah,
column?
we're taking from the search conducted column.
Search conducted. And
Yeah.
where are the original data with that? What it means, the search conducted?
Yeah, so the idea then, so basically if you look at this, so DF, search conducted. Okay, it's a true false column. Okay, so basically what we're saying here is that if you look at each of the individual cities, this is how frequently the value true came up for each one.
Okay.
Okay, so search conducted just tells you if that particular person was searched or not. And so in Winston-Salem, someone was searched about 2% of the time, and then someone here in like Durham was searched about 6.5% of the time.
Yes, I understand this, but I'm thinking about when we are taking or counting these as a mean of some value. Is it possible that two different cities will be coded to the same value? How we can do
I don't know. It should not work like that because these are all unique stuff, so they have to get encoded as one versus the other. And it would be encoded as the way the what jurisdiction it took place in. I don't know if I could actually guarantee it, but from the way I understand the records are supposed to have been kept, then basically it would be one search per one police district, which would be associated with a particular city. So I don't think you'd have the case where like a single police stop and someone got searched might get applied to simultaneously to multiple cities at the same time.
Okay.
Yeah, these are unique stops, as far as I know.
I know that we need get unique values for this because we are coding cities with these numbers. I just didn't understand how this method works with that to get different numbers, but it's probably said there.
Yeah, I think maybe to rephrase Sylvia's question, just for target encoding in general, how do you guarantee that target encoding will produce unique values?
Yeah, it was my question. Sorry.
Okay. I'm still not sure I understand. How do you guarantee it'll produce unique values?
Right. So let's say the like Charlotte and Durham have exactly, just by pure chance, have exactly 5% stop rates or search rates.
Yeah.
Then would a target encoder say 0.05 for both of them? Like, would it be possible to assign like the same encoded value to both?
Yeah, no, it doesn't actually specifically try and create unique values for that. So if like Charlotte and Durham were both exactly 0.05, they would get assigned the same value.
Gotcha. Okay. So to the model, they would be basically the same, which I guess makes sense.
Yeah. It doesn't explicitly look at like a unique categorical value. It's really just looking at the average value for that particular thing.
Gotcha.
Thank you. Thank you.
Welcome. Okay. Thank you, Jake, for being my translator. I appreciate it.
Sorry.
No, don't apologize. Yeah, no, thanks.
Good question.
Yeah, it's a good one. Yeah. Okay. All right. Everyone good? Okay.
Yeah.
All right. Yeah. Okay. All right. So anyways, that's where these numbers are coming from. Thank you, Jake and Sylvia, for the clarification. It's much appreciated. And then, all right. So we've got this. I'll get rid of the stuff. Okay, right. So this is our encoding pipeline. So Jake mentioned this before. It's useful to point out. If you're doing early stopping, which we're gonna do over here, you cannot actually put a pipeline inside the model itself. So maybe in some sense, it's a little less convenient. But what we're gonna do here then, okay, we're basically gonna go ahead, encode the training set, and then use the stored values in the training set to transform the validation set over here. All right, so go ahead, let's run through this. All right, and then the idea here, okay, so these values over here, X train, okay, Y train, right? You can see some of these are one hot encoded. Some of them though are target encoded. One more thing, Sylvia, sometimes is sometimes it can be useful to save the one hot encoding where you really want to study the effect of a single unique value. Okay, so in this case, you know, kind of the point of this exercise, one of the points is not just to kind of capture how accurate can you predict, you know, police, you know, searches or arrests, but also what's maybe the relative impact of, you know, being white, black, you know, Hispanic or unknown or something like that. And so in that case, it can be useful to make sure you have a unique column for each label, because that way you can study the unique impacts of each of these individual values more carefully than if everything were target encoded. Okay, so basically in this case, the subject characteristics that we want to make sure we can sort of isolate were one hot encoded. Okay, but for the other things like the stop reason and then the city, these were target encoded because personally I just have less of a motivation for looking at the relative impacts of these ones with a lot of granularity. So I just target encoded them. Okay. Okay, so we're gonna go ahead and fit. So we're using XGBoost, right? So we're fitting on the training set, okay? The evaluation set we're providing right over here, all right? Jake, I assume you have hopefully at least some passing like recollection of what boosting does. Some of the details, I mean, I'm be a little vague, but it's kind of like some basic idea behind it. Sylvia, you haven't taken it particularly, but this is usually the primary technique we spend time discussing. It's a machine learning technique that goes through several rounds of modeling, and every single round, it actually applies new sets of weights to each sample, depending on how hard that sample is to classify, okay, based off the previous round, okay? And so the idea, and it's kind of a stepwise iterative technique that will gradually pay more and more attention to hard to classify samples, okay? And so the idea then here, what we're doing is after every single round of training, okay, we're going to score the model, okay, on the validation set right over here. And then this argument means if we go at least 20 rounds without improvement on the validation set, the model is going to turn itself off. Okay. And then how we're going to evaluate the model is something called area under the precision recall curve, okay, which is probably what we're going to talk about next, okay? But before I do that, Let's just see if we have any questions. I'll wait till Jake looks like he's done looking at his screen. I actually mean that sincerely, not sarcastically, things like that. You know, like, I'll wait till you're done looking at your screen, you know, and then.
I guess, so I already ran that cell, and I'm looking at, like, so round 0, there's validation _0, and validation _1. Are those the two outcomes, essentially?
Yeah, that's training set and validation set.
Gotcha.
Yeah, you training score, the validation score. In boosting, the training score basically always goes up.
Yeah.
Like, you'll never not really improve your training score.
Okay. I'm just surprised that this is validation _0 and then validation _1.
Yeah, it just labels everything as a validation set and just sort of automatically labels it.
Okay.
Hey, okay. Real quickly here. Okay, so if you run it, yeah, you'll see a bunch of gobbledygook. Real quickly here, something that's probably worth kind of talking about here in a little bit. So if you look over here, okay, where we have the evaluation metric, okay, AUC PR, okay. This I actually think is probably one of the more important details of the whole exercise. All right, so the idea here is most people don't get searched or get arrested. Okay, so what we're looking at doesn't happen very often. And so a lot of times if you're doing classification on imbalanced data, kind of having the right metric to use can sort of impact your results. I've talked about it before. Lots of times just brute accuracy is not always the best approach if you have imbalanced data, because you know, if you just kind of predict no one gets searched, you know, you'll be right 97% of the time. Okay, so it doesn't really tell you very much about like what's actually understanding of what's causing someone to get searched. So a lot of times, you take some additional measures to kind of quantify how you're doing. This is kind of a fancy metric. It's a little hard to understand, but it is one of the better ones for imbalanced data. So the idea here, I'm gonna go back to my spreadsheet. Okay. We were talking about precision and recall. Okay, precision and recall is precision. Okay, also called positive predictive accuracy. Okay, basically says total amount of guesses you got correct. Okay, divided by the total number of guesses you made for that class. Okay, recall is the total number of items you correctly identified, okay, divided by the total number of items that actually occurred within the data. Okay, so kind of like a plain English way of thinking this, if you make a prediction for something, how likely is that prediction to be correct? Okay, of all the instances of something that occurred in your data, how many of them did your model catch? Okay, and so these two are kind of a natural trade-off of one another. Okay, the F1 score is a blend of this. Okay, which is just kind of this number times this number divided by this number plus this number. And so the idea here, if you're multiplying these two numbers, which are going to be between 0 and 1, okay, your score will do better if both of them are roughly equal. Okay, so a simple example of this, 0.5 times 0.5 is better than 1 times 0. Okay, so the idea then, this is kind of give you, it'll basically reward models which kind of balance these two trade-offs relatively well. Okay, average precision score, or area under the precision recall curve, okay, is something a little different, but it's closely related to this. Okay, so the idea then, okay, what you do is you look at your predicted probability. And then for where you predicted this particular probability, you actually use this as your cutoff point, okay, for whether or not something was true or not. Okay. And then you look at the precision score, it might be something like, I don't know, 0.9. Okay, proba 0.1, 0.8, 0.2. Okay, 0.85, 0.3, 0.75. Okay. All right. So the idea then, all right, what you do is you look at your precision, okay, at different probability thresholds. Okay. So the idea here, when you calculate an F1 score, basically what you do is you're using 0.5, okay, as the cutoff point. You know, like if your model predicts is over 0.5, you know, you say that's going to be a positive. And if it's less, then you say it's going to be a negative example, right? The idea is a lot of times what you might care about is how your model performs over all probability thresholds. Okay, so the idea then, what you do is you might actually, instead of using 0.5 as the cutoff, you use 0.01 as the cutoff for whether or not something's going to be positive or negative. Okay, and then you look at the resulting precision, and then you increase this right over here and do this, increase this right over here, do that, increase this right over here. Okay, and then what you do then is you gradually do this. You can actually use as many thresholds as you want to. And then you look at the actual precision across all of these different decision boundaries, and then you average them up at the end. Okay, and that's the average precision score. Okay. It gives you the benefits of kind of seeing how your model performs and how sensitive it is across all areas of prediction versus one single hard decision boundary. Okay, and so soft boundaries like this can actually kind of give you maybe a slightly more holistic view for how your model performs under a wider range of circumstances. Okay, and it's generally true at a lower probability threshold, precision will probably be higher, and then recall will probably be lower. And then the higher your threshold goes up, usually the higher recall will be and the lower precision will be. Okay, so it kind of does something very, very similar to the F1 score, but it's actually a bit more thorough in testing for it. Okay, in terms of like the balance between precision and recall. Okay, I don't think it's literally the integral of the F1 score, but I think it's sort of more or less, it's kind of basically works in about the same way. Okay, so when you see this average AUC-PR, what it is referred to as, so I can find it, area under the precision recall curve. Okay, because the idea is if you were to plot precision versus recall at different probability thresholds, it would be the total area under the curve. Okay, and that's kind of what it's calculating. Average precision is kind of like basically it's kind of a synonymous way of doing it. Okay, but it's actually a pretty good way of evaluating a classifier and imbalance data. Okay.
Interesting.
Questions?
Is there like a visual that you have to go with that curve?
Right now, I don't, but literally, it is actually a plot you can kind of go ahead and pull up to like literally see like how it works.
Okay.
So probably later on, if you won't mind, afterwards in Slack, I can post something like little snippet for it or something like that. But yeah, literally, like there is literally like a curve you draw, and like it's literally like the shaded area underneath it.
Yeah. Okay. Cool.
Okay. Yeah.
And are we setting somewhere how many points we are using for this evaluation metric? Like you were making about 20 of them, or it's some kind of.
Oh yeah. It is built. Yeah. So basically, how many different thresholds do you actually use?
Yes.
In order to sort of figure it out? I would have to go ahead and double check. Like the pure measure of it is like you literally use like every single one. Like that's the integral. Like you kind of like sum up everything. I think in practice, I'm not actually entirely sure how much it uses. Actually, let me backtrack a little bit here, Sylvia. There are two different ways of calculating it. There's something called the trapezoidal rule, which actually doesn't use individual boundaries, but rather just sort of like uses a separate formula to literally calculate the area under the curve. And then the average precision score, which is the one I sort of walked through here. This one actually does use a certain number of boundaries. I would actually have to look it up though to see how many it uses. I'm not entirely sure, to be honest with you. Okay, so consider it a point for follow-up, okay?
Okay.
Okay, thank you, Sylvia, good question. Okay, let me just take a quick look. I just used the default here. I just want to check here the documentation, average, label. Okay. It doesn't look like it's an actual argument that you can specify. Okay. But all right. We'll just kind of leave it there. Okay, for now, yeah. And I will go ahead and take a look. And then later on, Sylvia, I'll follow up with you, okay?
Okay.
Okay. No worries. Okay. All right, so in any event, okay, so this is the metric that we're using, okay, which is kind of a slightly more holistic way to look at the trade-off between precision and recall. We run this thing. Okay, so you run this thing, all right, we get the output every subsequent rounds. Okay, so the idea is, okay, when we go, at least 20 rounds without this number improving, okay, it turns off. Okay, the best round was 139, so we'll go ahead and we'll change that right over here. Okay, and then AUC-PR, average precision score, are essentially synonymous metrics, but in scikit-learn it's called as average precision score, and XGBoost it's called AUC-PR. I actually do think they're calculated slightly differently, but it's not that dramatic. Okay, so average precision score, okay, off the validation set is 0.199. Okay, and then what we're doing then is we're refitting it on all of our training data and then getting the test score. Okay, it actually comes out a little bit higher, which is nice. Okay, and then here we are. Okay, other steps are taken later on to kind of find values for other parameters. But in terms of kind of where like 80 to 90% of the results came from, it was using early stopping on validation loss, using the average precision score as the metric. Okay. There are more details added in, but in terms of like the modeling, these are probably like the most important things. Okay.
Yeah.
Jake, hopefully this felt somewhat similar, things like that. We didn't cover AUC-PR, average precision score, but it's kind of like it's kind of related to F1, precision recall, things like that. And then Sylvia, happy to answer any questions if there's something you're not quite sure on.
I was trying to run the cells, and I'm good until I get best iteration 139, but after that I'm getting error.
Okay, can you share your screen with me real quick?
Sure.
Okay. Okay, all right, looks good. Okay.
And when I'm running this, I'm getting this error.
Okay. Oh, it says not fitted error. So that means you literally didn't fit your model yet. So scroll up. Okay, scroll down. Okay, so in cell 12, yeah, run that thing.
I ran it before.
Okay, so let this go. And then after that, you should be in good shape.
Because I ran it 2 times and I got the same error.
All right. we'll see here, okay? But like mod fitted literally means
I'm here.
that thing just literally you haven't actually trained it on your data yet.
So does it mean I skip one cell before?
It probably just means you skip the cell. All right, so try that one when it's done. Okay, looks like it's done now. So try scroll down and then try where it says mod best iteration. All right, and try the next one. Yeah, there you go.
Oh, okay.
Yep,
Thank you.
you're cooking with gas. Yep.
And now I have to stop sharing how I do.
Okay.
Oh,
All right, great.
Thank you.
You're welcome. All right, Jake, any questions?
The only question I think I have is so when we import the sklearn.metrics and then go for average precision score,
Yeah.
We were already using that when we were like calculating the training and validation scores in early stopping, right? When we were actually fitting the model.
Yeah. The only reason I did it that way is because for evaluating the test sets, you need to do that separately. And then just to make sure they're exactly consistent, I use like the scikit-learn method on both.
Gotcha.
Okay, actually, because I actually think in an XGBoost, there are two different ways of calculating the average precision score. I actually think they use different ones. And so it wouldn't make a big difference, but they might be off by a couple percent. Okay. And so just to make sure like the comparison between the two was consistent.
Okay, so it's mostly the variation between the two libraries and how they actually implement.
Yeah, how they calculate it. And then I don't think there might actually be a way to provide like a custom scoring metric inside XGBoost when you fit, for like the eval metric, but I didn't go that far because it was easy just to go ahead and do that instead. Okay.
Yeah, thanks. I was missing that it was like two different libraries there.
Yeah, that was the reason why. Okay. So that is basically it here. If you guys want to continue to work on this, today or later on, if you want to go into the notebook for the lab, and then you probably just mentioned how much time you had and things like that. But the idea here, okay, this is kind of what was more or less done, okay, to get the results, stuff like that. Some additional stuff was added on, but there's probably no more than a 5% difference based off of what was done right over here. So if you go into the lab,
okay.
If you go into the lab here, let's try and find it. Okay, it's somewhat open-ended, but the idea is if you wanted to, you could go through any of the 4 different scenarios and then the columns that are used. And you could use gradient boosting if you wanted to, but if you want to try something different, you could go ahead and then try that as well. Okay, and so the idea then, you can maybe take a crack at recreating some of the results and perhaps modifying a few things, to see what would change for one reason or the other. Okay, and then you have the columns you should use for target and input, and then also the baseline score for what was actually used inside the app. Okay, to give yourself kind of a feel for how you're doing.
Mm-hmm.
Okay, which is basically the test score. Okay, so and then again, you could use the notebook as a guide if you wanted to, just to kind of like brush up on some things, and then we could do that for as long as we wanted, or until actually for about 1 hour at max, because that's when I have to go. Things like that. But if you wanted to go ahead and go into that, that's cool. And I could answer any questions when you guys are done.
Okay. I guess the one question that I have just kind of off the bat is you list 3 choices of model here, and Ridge Lasso is one of them.
Oh yeah. So for whatever it's worth, a small history of that, Jake. So originally in the very first version of the class, I taught linear regression, and then Ridge and Lasso are specialized versions of linear regression. And then also we covered random forests. So it was like so linear regression plus random forests. Okay. Then eventually I switched to XGBoost about 1 year ago. Because to be perfectly honest, XGBoost is actually, gradient boosting is the higher performing model. Like about 80% of the time, it would actually give you better results. So it is actually like the more appropriate choice, you know, for giving like most contemporary things like that. But usually the case, the people who come here, actually the majority of them actually took DAT using those versus gradient boosting.
Gotcha. Okay.
So just people who could use whatever thing they're most familiar with to try and go ahead and recreate stuff.
Okay, cool.
I'd actually be surprised though if any of them actually outperform gradient boosting, whatever it's worth. I haven't tried it myself, but I would be surprised if they were better.
Okay. Cool. Nice.
Yeah. Okay. Anyone else?
No, I'm okay. I see that I am really behind, so I need to go again from the beginning.
Yeah, Sylvia, in your case, I would actually probably just try and recreate the notebook itself and just kind of walk through steps and see if you can, you know, just kind of grok like why each thing was placed there and things like that. And then if you have any questions about it, you know, just put it in the chat and then I'll be happy to tend to whatever I can.
Okay, thank you.
Yeah, no, that'd probably be my best recommendation. And then obviously certain things won't be clear to you. But you know, getting the error messages here live will be better than getting them later on.
Thank you.
Yeah, sure.
And next week we will, not next week, next 2 weeks we will continue on this project, but it will be
next actually at least 3 more classes. We'll actually just keep on with this project.
And you will count something different or different model you will make from this?
Yeah, we're actually gonna so this one we're gonna kind of go over like how it was done. Later on, we're going to talk about how to interpret the results. Okay, so there are 2 things, like the predictive modelings, like what are your chances of like arrest or search and things like that. But also here, another part of the project, I was using some newer techniques, Sylvia, to actually deconstruct the model into its core contributions in terms of all the individual columns. And so so there's a separate software package called SHAP. And so we'll go into that. And then finally, that'll probably be at least 1 or 2 classes, Sylvia. And then finally, too, is there was a different technique that was used to actually choose additional model parameters. So early stopping was used for define the number of boosting rounds. But then there was a different technique that was used to find other parameters that you can use for XGBoost. Okay, and so we'd go over that at the end.
Thank you.
You're quite welcome. So it's sort of more like not just like different. Honestly, most models would probably give you about the same results. Like maybe not radically different, you know, but like within like 5% or so. And this is probably going to be the one that gives you the best results. So we're just going to talk about this one and then go on to other parts of it.
Thank you.
You're quite welcome, Sylvia.
And are you going to make this video? Are you going to post it on?
Yeah, this is actually being recorded, so it's going to get posted.
Okay, thank you.
Yeah, no worries. I actually forgot to do that last time. I think just due to some kind of technical, like a slip of the mind. You know, I thought I pressed record, but it didn't. So it just went into the Netherlands. But yeah, this one's being recorded. I can see it now. Okay. I'm probably actually gonna stop recording because this is probably like all that's really, you know, fit for public consumption. So I'm gonna go ahead and go off here. So same thing. All right. So stop recording.